from Croatia. She will present Raman Spectroscopy Technique and specific application for study of ceramics.
Good morning, ladies and gentlemen. I come from Boscovich Institute for Molecular Physics Laboratory. Our laboratory started with Raman spectroscopy already 60 years ago. So even before I was born, or well, most of you was born. So this is the reason why Professor Vladimir Serdic kindly invited me to present basics of Raman spectroscopy. As I know, they have also new Raman instruments, so I prepare my talk basically as tutorial, but I will also show some examples from our practice. First of all, I would like also to thank organizer, especially Vladimir. He is not here, but you can tell him to invite me to come here and see your beautiful town. Okay, so in the first part I will speak about the basic principle of Raman spectroscopy and some instrumentation, experimental setup, and some different way how to achieve good results and what we should do, what we should not do, and so on. And in the second part I will present most of this work is from our laboratory. I would like just to mention soft mode ferroelectrics. This is not my main field, but it is important for people who work with the ceramics. So let's start with my basic principle. First of all, I would like to start with the spectroscopy, because this is the background of our method. So definition of spectroscopy is that it is interaction of the electromagnetic radiation with matter. So during this process we have emission, absorption, inelastic scattering. But always we have Bohr condition which should be satisfied during such processes. So the energy of incident light should be the same as different in energy levels which we investigated. Since in the Raman spectroscopy and also in the infrared spectroscopy we usually speak in the frame of wave numbers, so this is a relation between frequency, wave numbers, and wavelengths of the light. So there is two basic transition in this molecular systems or crystal systems. This is electronic transition, which usually use UVVs or XPS, UPS spectroscopy to study such transitions. They are vibrational transitions, which can be observed by infrared and Raman spectroscopy, and there is also rotational transition, where we use mainly Raman spectroscopy and microwave spectroscopy. Since I will have much more time than is predicted, I will show a short animation just to show what is happening between energy levels during any of this spectroscopy. So in the case of infrared, we have only a transition between the different vibrational states of the system. In the case of UVVs or any other electronic spectroscopy, we have absorption of photons and transition to excited electronic states. In the case of fluorescence, we also have absorption, but we have also vibration of the states, and then energy levels dissipate. In the case of the scattering, which I will talk about, we have really scattering where the energy of the incident photons and emitted photons is the same, and this is Stokes process, which we will observe by Raman spectroscopy, and anti-Stokes process. Both of them use the incident light to excite the system, but we have different processes, as I will tell you later. So what is actually Raman spectroscopy? This is scattering. This is not real spectroscopy. We have incident photons which interact with the molecular system and the electric dipole of the molecule, so we after that have the scattering. as I mentioned, this is usually Rayleigh scattering, which can be easily observed because this is elastic scattering, and when we do spectroscopy, Rayleigh scattering have a very large intensity. In the Raman spectroscopy, this is inelastic scattering, so a fraction of light is absorbed by the system, and this absorbed part of the light is actually what we are recording. So we will have Raman effects, which is first observed in 1928. Raman, I cannot pronounce his name, but he got the Nobel Prize for this effect, even if he didn't understand what is going on. Later, people explain what is actually Raman scattering. So these are our processes during the scattering. So we use incident laser line, which can induce transition to some virtual states which actually doesn't exist. But after that, we have scattering with lower energy, and this is Stokes-Raman scattering. We usually look only at this part of the spectrum. But there is also the other process where the light is absorbed at the excited vibrational state, and we have scattered photons which have larger energy than incident photons. And we can observe also anti-Stokes part. But these intensities are much smaller because the population of the level of the molecules. So this population of the levels of the molecule is proportional to the temperature. So if we compare intensity of Raman scattering of Stokes lines and anti-Stokes Raman lines, we can also calculate the temperature during recording our spectra. So we can know what is going on during the recording. It is important because sometimes if you have very intensive light, then you can heat your samples. So you can even, during the recording the spectra, you can have phase transition not because of any other reason, but because of the laser line. So sometimes it's extremely important to calculate what is the temperature during your recording the spectra. Okay, so here I would like also to stress the infrared transition. Infrared is direct transition between vibrational states, and it is complementary to Raman spectroscopy, as you will see later. So when I speak about Raman spectroscopy, I can speak from different kind of point of view, from instrumentation analysis, type of analysis, Raman measurements. So Raman spectroscopy have a huge possibility. But I will speak today mainly about useful of Raman spectroscopy for inorganic solids. Since one professor asked me, why you use this strange method to study our ceramics or nanoparticles. I will explain you later why it is important sometimes. And sometimes you can have much better result than with other techniques. I will speak about laboratory measurements and mainly about qualitative measurements. I will mention also phase transition in high temperature. And since usually in a laboratory praxis people use dispersive instrument and multi-channel detectors, we have also such instruments. I will mainly speak about such instrumentation, but I will mention interferometric system. So what is actually happened during the Raman scattering? We have incident light, and then light push our system. Here is example of methane. And our molecule or crystal, if you speak about ceramics, start to vibrate. But the system can vibrate only in some specific modes. They cannot vibrate in a different kind of strange way. So we have so-called normal vibration. So this is actually our vibrational modes, which we can observe either by Raman spectroscopy or by infrared. So if we have some more complicated molecule, we will have much more vibrational normal modes, and all of these modes are actually bands in our Raman spectrum. If we have crystal lattice, as is the case in ceramics or any crystal system, with n atoms per unit cell, if we would like to have mathematical description, we should use a very complicated system with the free n equation of motion, which also include different kind of vibration, but also some just shifts in the system. Such kind of system of equation can be diagonalized. So by diagonalize this matrix, we have solved the problem, and we will get so-called normal coordinates. Actually, these normal coordinates represents our modes. So when you get this diagonalized matrix, you will have a mathematical representation of every of your modes. However, not all modes will be observed because of symmetry of the molecular, which dictate different selection rules. So if we would like to have or observe infrared active modes, dipole moments should change during the oscillation period. In the case of Raman active modes, we have element of polarizability tensor which change during the oscillation period. But we also have some silent modes which cannot observe with any of these methods. I should just show shortly this induced electrical polarizability tensor should be different than 0, and it is proportional to symmetry of the molecule. Now it sounds very complicated, so I also find some animation which will show you visualize this equation. So for example, if we have different molecules, in the case of carbon dioxide, we have center of symmetry. In such molecules, infrared and Raman spectroscopy active modes are complementary. So if we will have modes like this is bending mode, then polarizability will not change when the molecule went through the equilibrium position. So this mode will not be Raman active. So complementary, we can observe this mode in infrared spectroscopy. So it is infrared active because dipole moment would change. This is the other kind of process. In this stretching mode, symmetric stretching, we have change of the polarizability of our molecule, but at the same time dipole momentum will not be changed. So such mode would be observed with Raman spectroscopy, not with infrared. So very often we use both methods to study some, especially the system where we have a center of symmetry. So for example, water, it is not central symmetric. So in this motion, vibration of the bands of atoms in the water, we will have bending mode, for example, which is weakly Raman active, and this mode will be very infrared active. So this is one of the reasons why the Raman spectroscopy is very useful for study liquids which have a lot of water, since the Raman spectroscopy didn't have very strong bands of the water, so it is very suitable to study, since in infrared you will have strong bands of water which could cover the rest of your sample. Okay, so this, for example, this one is strong Raman active and is also infrared active. So actually we use such representation just to understand what is going on during our spectroscopy, and from symmetry of the molecular, using the group theory, we can calculate how many bands we will have in our spectrum. But all bands don't need to be observed, because sometimes you have overlapping of the bands. Sometimes you haven't got enough intensity to observe some bands, but point groups will give you just idea what you should expect. The other things which we would like to know sometimes is position and intensity of Raman bands. For such calculation, this is not simple as is X-ray diffraction. So vibrational energy levels of the system should be observed, should be obtained by solving the vibrational problem. So you should go deep in the theory, use some approximation and calculate. But there is a lot of data about Raman spectra, so there is also database, and some things is well known. For example, even if you think classically, if you have larger atoms with larger masses, then your frequency will be, of course, lower. If you have smaller masses, your frequency of if you think just about vibration, then your frequency will be larger, especially when you think about bond lengths. If you have long bond bands, then your frequency will be lower because the motion will be slower. So there is idea you can predict if you have some complicated system, for example, some mineral with a lot of atoms of different sizes and forms, you can just recognize which kind of environment of some atoms you have in your system. And there is also well-known position of the bands vibration for some bonds between oxide and the different metals. So of course the position also depends of environment. But when you start spectroscopy, you can have some idea. For example, if you have a very light element, for example, in some organic substances, all your bands will be at very high wavelengths. If you have crystal, for example, some inorganic crystal, you will always see this crystal part of the spectrum. So what we are also interested in is the intensity. So there is different factors which influence the intensity, but it's important to stress that intensity depends on even fourth power of your laser light frequency. So for example, if you use red line, excitation line, or even infrared, there can be possible that you cannot observe some vibration because the intensity is so low that it cannot be observed. However, if you use, for example, green line, which we are using usually, or blue light, then you can have a much larger intensity. But sometimes, due to the energy of your laser, in some systems, if you have electron levels which are very nearby, then your laser will induce excitation in electron states. So instead of Raman spectrum, you will have just a large, broad peak of fluorescence due to the electron transition. In this case, it's better to use red line. So sometimes we should have some prediction what we should do, which line we can use, especially if you have possibility to use different lights. So I would like also to compare Raman spectroscopy with other techniques which are usually used. So Raman can record very small samples, about 1 micrometer, especially if you use micro Ramans. So you can go, if you have some mixture of different materials, you can record it very carefully. While for X-ray diffraction you need much larger volume. A range of order which is probed is less than 5 nanometers. So you will also observe some vibration if you have very small nanocrystals. You will also observe short range ordering in the case of glasses. So Raman spectroscopy is especially interesting for amorphous material, because if you have any kind of let's say, chains in glass or whatever, you will see in Raman spectrum some bands, and from position of the bands and a number of the bands, you can have idea how your glasses or amorphous material looks like, which is not impossible to observe with X-ray diffraction. It is also very sensitive to crystal symmetry, as I will show later. For example, if you have small tetragonality in your system, and X-ray diffraction is less sensitive only if you use synchrotron radiation. And of course, Raman spectroscopy is a much faster method. If we compare it with infrared, as I already mentioned, water is weak Raman scatterer, so you can record the liquid samples, we can also record gases and so on. And the selection rules will not show all vibration in infrared, so Raman should be used. And in principle, Raman can also study rotational states, magnetic states, electronic states, magnetoelectric states. I mention in principle because the rotational states are at very low wave numbers, so you should have a very good instrument to observe this part of the spectrum. But there is also disadvantages. Every method has disadvantages. So as I already mentioned, laser source is needed. So you can have local heating, you can have already mentioned phase transition, and fluorescence, as I mentioned. We have indirect information. You saw that you should solve the huge amount of equation, but usually when we are using Raman spectroscopy, we have some database and we can compare. As when you do X-ray diffraction, you have database, so it's much easier. And the instrument is more expensive than infrared, however, it is similar as diffractometer. Now I will switch to instrumentation. Since I already mentioned, there is dispersive Raman system and Fourier transform Raman system, which have different kind of physical data. So when we start with dispersive Raman system, we have sample, we have laser, and we should focus our laser line to at the sample to excite the vibrational, and we have spectrometer. So this spectrometer can be different, and detectors can be different. You can have CCD camera, you can have photomultiplier, and it depends. And collimator optics can also be micro Raman microscope and so on. In our laboratory nowadays, we use very modern Raman instrument. We use argon-neon laser, but sometimes we also use some other laser, some red laser, which is solid-state laser, and so on. We have this micro chamber with confocal microscope. So we have also stage which can move, so we can do Raman mapping. We have a large macro chamber. Now it's closed, but this closure can be removed, so we can attach different cryostat and so on. But I would like to mention that earlier we have different system. We have just triple monochromator without micro Raman part. Even before, I have never seen this instrument. They had some Russian instrument, which was also very good. And at the beginning of the laboratory, our lady, she is already died. She made by herself a Raman instrument. So they have very, very long tradition. So for our instrument, we have different attachments. This is a microstage which can measure low and high temperature. We have heating stage. Here you see the picture where it's attached to our old instrument. We have two cryostats with different temperature possibility. But I would like also to stress some things which we should take about during our measurements. we should optimize the scattering chamber optics, because the Raman scattering is even 10,000 times lower in intensity than Rayleigh light. This is the reason we have always Rayleigh line. So we should cut the wings of this Rayleigh light to get Raman scattering signal, especially if we would like to see at very low wave numbers. So due to this reason we use double or triple monochromator. Nowadays there is also some filters which just cut a line, Rayleigh line in single mode. We also can use our instrument in single configuration. However, when you cut it, these Rayleigh lines, you will always cut part of the Raman spectrum. So in this case, you should be careful not to lose your signal, your data, and so on. And this is one very old result of my boss. He is already retired for 7 years, but he measured temperature. As I mentioned, there is a large increase in temperature during recording. So he checked what was the temperature in the laser focus when you change the power of the laser, but also if you change the size of your particles. So he observed that if you decrease the sizes of the particles, the heating is much higher. As I mentioned, he calculated from intensity ratio between Stokes and anti-Stokes, so he found very large heating. For example, he used silicon grains, even with very small laser power. So this is the reason why we should be careful. We should know what we are recording actually. Do we recording our sample, or did we burn our sample and record something completely different? And we can avoid such a problem. Partially it can be avoided by polishing the sample surface. We can rotate sample. We can use, of course, low laser power, but then you will have a lower signal. However, if you use high accumulation times, then you still can get signal. You can use also cylindrical lenses to produce the line focus, not the point focus. So then then you will avoid heating. And there is the other things. If we do high temperature measurement, we should check thermal population factor and correct the spectrum before we do any peak assignment. Sorry. As I mentioned, nowadays most of the Raman instruments have micro chamber. So in a micro chamber you can measure point spectra for different substances, but also mapping is possible. If you have some complicated system, you can see which phases do you have in the system. And especially it's useful to have confocal Raman, because confocal system, if we use confocal system, we have very small focus. Therefore, if we have multi-layer sample, for example, but sample of course should be transparent, otherwise you cannot come with your laser in deep in the sample, then you can do deep profiling and measure your layers in the sample. And at the end, I would like just to show the system, how it looks like if you have a Fourier transform Raman instrument. It uses interferometer instead of spectrometer, and such instrument is much cheaper than dispersive spectrometer, and usually is attached to infrared instrument. However, this instrument is also good because it reduces fluorescence, because in such instrument infrared light is used for recording spectra, but sometimes you cannot observe your lines because the intensity is too low. So this is good instrument if you have no money, just to have idea what you have in your system. because you can attach it, and the other things, you can have idea, but also the spectrum is much lower in intensity. It is in better, worse quality, but also the spectral resolution of such instruments are usually 4 inverse centimeter. In our case, spectral resolution is 0.1 inverse centimeter, so sometimes you cannot recognize your lines. So in the second part, I will talk about different examples. I choose just a few measurements which is connected maybe with ceramics. So as I already say in the beginning, I will just tell a few words about soft modes in ferroelectrics. When we have ferroelectric transition, then we have the break of central symmetry, so we don't have cubic structure. Usually cubic structure have either one Raman band or have no any vibration. And after ferroelectric transition, optical phonons become Raman active, and you can also see the phase transition from ferroelectric to paraelectric state. And hard mode phonons appear or disappear during the structural phase transition. So this is one very old example. This is for the first time where the softening of the mode was observed. So it was in the case of lanthanum aluminum oxide. So authors check the shift of the modes during the heating of the sample. So they observed that their Raman bands shift to lower wave numbers during the heating of the sample. So in the same time we have the shift, the change of the structure, so the tilt angle in the crystal change. So they even calculate the tilt angle at any temperature, at every temperature, and after 800 degrees centigrade they get cubic structure of lanthanum aluminum oxide. Now I will speak about our own results. So now I would like to show why we use Raman spectroscopy as a better choice for instrumentation. So this was the study of the barium titanate nanorods, which was produced by chemical processing. And in our nanorods we observe different phases. So we observe the bands of cubic structure, but also we observe tetragonal phase. We observe also some impurities, but it's all important to mention that such nanorods had the bands which belong to hexagonal structure. But hexagonal structure is high temperature structure, and this was some kind of surprise how the tetragonal structure can appear at room temperature. These two bands are for comparison. This is nanoparticles of barium titanate and microparticles. So normally there is no hexagonal structure in such samples. However, also X-ray diffraction measurement was done at all different nanorods, but using the X-ray diffraction there is no observation of any tetragonality, and especially they didn't observe a hexagonal structure. There is a few reasons because of this. There is a very small amount of hexagonal structure which cannot be observed by X-ray diffraction, and as I already mentioned, tetragonality in barium titanate is very small. So you actually have a ratio between C and A axis which is just very small, so it cannot be resolved with X-ray diffraction. This is the example of one of the line. So in such system, Raman spectroscopy was shown as a better method of choice for such a study. So we also studied the phase transition, the most important phase transition in barium titanate from ferroelectric to paraelectric state. So we observed that the tetragonality still exists at much higher temperature than is expected. So we observed both bands of the which belong to tetragonal structure at much higher temperature, but this hexagonal band was still here. Somebody can say maybe this was the some mistake, maybe this wasn't a hexagonal structure. But later on, high resolution measurement was done, and some kind of lamels was observed in our nanorods, and this lamel was really in hexagonal structure. So there is very small amount of these labels which was observed by Raman spectroscopy, and later on can be observed with high resolution TM. Of course, high resolution TM is even twice or third time more expensive than any Raman spectroscopy system. So, and of course you should prepare your samples. You should spend 1 day to find part at TM. TM and high resolution TM is really the best method for every study, but comparing to Raman spectroscopy, it's more complicated. This is one very old system which I studied at the beginning of my career. So I studied the phase transition in zirconium oxide. I studied also high temperature phase transition, but this was phase transition induced by stabilization of tetragonal and cubic phase. As you know, these phases have much higher resistance, especially tetragonal phase is the best for ceramics, for hard ceramics, for bone implants and so on. So in this time, this is still my maiden name, so this was very far ago. So we milled, prepared stabilized zirconia by high energy ball milling. So we try also to mill sample without any addition of any other oxides for stabilizing, and we milled it with cobalt oxide and with yttrium oxide. So what X-ray diffraction observed? X-ray diffraction observed that there is no any changes of structure. There is mainly monoclinic, and they observed some impurities of tungsten because tungsten carbide milling assembly was used. But after addition of cobalt oxide in the yttrium oxide, X-ray diffraction showed the same results. So X-ray diffraction measurement shows that we have a transition to cubic structure. However, with Raman spectroscopy, we can easily recognize appearance of tetragonal phase already when we milled pure samples. We actually explain this stabilization, but with inbuilt of tungsten in zirconium oxide. So actually, this is also stabilization. And after addition of cobalt oxide, we have very good tetragonal structure. However, this one was cubic. So using Raman spectroscopy, we can easily recognize difference between cubic and tetragonal structure. It is very easily understandable, because if you have cubic system and if you have vibration, they will vibrate symmetrically, just in one way. If you have something which is stretched, then you will have much more possibility of vibration, much more modes. So for tetragonal structure you will have 6 modes, for cubic you will observe just 1 mode. So such a system, this part of the spectrum I would like to mention is due to ball milling, which induced a lot of defects. So this is something what happened in the system with this, which have some defects. So in this case, Raman spectroscopy will show us a bit different results. However, we can use our instrumentation for measurement of some completely different phenomena. We measure luminescence property of yttrium oxide doped with rare earth, or we also can observe very small impurity of rare earth. What is going on? When you put rare earth oxide element, some ions in the crystal lattice of, for example, yttrium oxide and any other matrix, you will have stark splitting of f orbitals due to crystal field of your crystals. So even if you have, for example, one ion of the erbium or holmium or any other rare earth, in a whole large crystal with, I don't know, million of atoms, you will have stark splitting, and you can observe transition, electronic transition this time between f orbitals. So it looks in spectrum like this. This was yttrium oxide compounds, 99.99% purity, pure. So there is very small amount of earth oxide which produce splitting of f orbitals, and we observe a very intensive luminescence band in Raman spectrum. But how we can know that this is luminescence? Sometimes somebody can tell us, okay, but this is also Raman bands, maybe you have something else. However, if we change the excitation line, as I mentioned, we always observe just Raman shift. We have excitation line, and we have shift around your excitation line, and this shift, this band is actually just part of the energy which system grab for vibration. While when you have electronic transition, then electronic transition have fixed wavelengths. So if you shift your excitation, all Raman bands, which are mixed in this case with luminescence light, will be shifted. So this is part which is Raman active bands, and this is luminescence. So if we look at the absolute wave number, this luminescence band will be always at the same position after illumination, after scattering, while these Raman bands will be shifted. Every time we are looking only at the Raman shift, so our spectra will looks different, but when we compare them, then we can easily recognize luminescence line. So in this way you can, if you are not sure that you have really Raman bands, then you can just change your wavelengths for excitation, and then you will be sure. Or you can send it to your colleagues who have different lines. So this is the way how to recognize what is going on. So due to this reason, we use our instrument. This was collaboration with one colleague who had a Fourier transform Raman. So we made the whole study of the luminescence spectra in system like yttrium oxide doped with holmium. Later on we use different earths. So this our study is also important since we can easily resolve this band. Normally with the UV spectrometer you cannot resolve this f orbital transition so nicely. And now, as I mentioned, the Raman spectroscopy is useful for amorphous or nanocrystalline systems. So here I would like to present one study in collaboration with the mineralogical department with one very complicated metamixed system. Metamixed mineral, they are actually amorphous mineral, but amorphization happened due to nuclear reaction which happened inside the minerals. And this study is important for storage of the nuclear waste. So if you would like to storage your nuclear waste in some mines, in some rocks, then it's important to know the processes. So this was the study of fergusonite. Fergusonite have two different phases, crystal phases. but metamect mineral was completely X-ray diffraction amorphous. And after heating, these two phases can be achieved but by heating at different temperature. So mineralogist wasn't sure which one of these phases was the original phase. We try Raman spectroscopy, and in unheated sample we already observe some short range ordering. Well, the position of this band belonged to niobium tantalum oxide tetrahedron vibration, so we concluded that it should be alpha fergusonite. Of course, we wanted to check our findings, so high resolution TM was done. First of all, we need to have idea that we have something crystalline. Otherwise, you can look at SEM images and try to find something, and if you haven't got any prediction for crystal phases, you will not even try to find it. So using TM and electron diffraction, we find relics of original phases, and the relics show very easily that our finding with Raman spectroscopy was true, and that we really had alpha fergusonite. And after heating, beta fergusonite can be formed, but originally this is a system which, of course, different system, beta fergusonite and alpha fergusonite is not the same if we compare it how they are behave in the presence of nuclear waste. So this was the further study, but I will not bother you with this. At the end, I will just briefly present result of some bioceramic system. We can use Raman spectroscopy to check phase formation during the study of calcium phosphate. So when we use calcium phosphate system, and when we would like to achieve different phases of calcium phosphate in solution, we need different time to prepare amorphous calcium phosphate, octa calcium phosphate, and hydroxyapatite. The study was devoted to different additives which increased the velocity of phase formation. This is still not published, so I will not show all details. So if we use Raman spectroscopy, we have the shift of the band maxima and decrease of band broadening during change of phases. So this is a starting system without any addition. So you can easily observe that after 4 hours, bands characteristic for octacalcium phosphate appeared, and we needed 2 weeks to formation of hydroxyapatite, since in this case the bands are much narrower and the shift is much larger. So due to position of the bands and also the bandwidth, we can conclude which phase we had. This is, as you see, TM observation. So of course after 1 minute we still have amorphous calcium phosphate, formation of octacalcium. Just seeds of octacalcium can be recognized as very small bands, and here you see morphology which belongs to such seeds, and after 4 hours or 1 day we already have a completely formed octacalcium phosphate. And this is the other study where we studied the deposition of calcium phosphate with ceramics. So we compared the part of the spectrum which belonged to calcium phosphates and part of the spectrum belonging to ceramics, and by increased time of in solution, we observed that after 28 days we have completely covered ceramics, completely covered with calcium phosphate. At the end, I would like to summarize. There is also a lot of other examples. I mentioned glasses, but I decided to skip them to have enough time. So I would like to summarize that study of crystal structure and phase transition can be very well developed with Raman spectroscopy, especially in perovskite material where the tetragonal phases haven't got so much difference between in comparison to cubic. Earth luminescence can be detected with Raman instrument. We can study amorphous or nearly amorphous material. But it is very important to stress that reliable results can be achieved only if you take care during your instrument, if you take care about intensity of your laser, about the position, about good focusing, and so on. At the end, I would like to mention some of my collaborators from our institute, from collaborating institution in Croatia. These are the guys where I'm going to do TM measurements, and there is some funding which was used for this study. At the end, I would like to finish, like most of the invited speakers, I would like to invite you to come to our Multinational Congress of Microscopy, which will be 2017 in beautiful Rovinj, in this very fancy hotel, but we already discussed with hotels, so the prices will be low, and also our conference fee will be low. And of course I will show the map. It is at the seaside in nice Istria. And at the end I would like to thank you.
Thank you, Professor Gajovic, for this very nice presentation, and I think very useful for, especially for young researchers. So, have we any question now? Yes.
Thank you for your very interesting lecture, and I was wondering if you could tell us something more about quantitative analysis. If it is possible, and if yes, how reliable it is for this kind of research.
This is possible, but for quantitative measurement you need to have standards. Because I skipped one part. It's even further. For example, here we had a mixture of zirconia and titania, and even it was equimolar mixture. You can see that bands of zirconia is very small and bands of titania are huge. So if you would like to have idea about what is going on, you always should have standards. So you should prepare your mixture exactly of two different phases or what you would like to study, and do the Raman spectroscopy measurement.
We have to calibrate some.
Yes, so then you will get calibration.
And then if we have all the calibration and everything, how reliable are those results?
It is very reliable if you compare relative intensity. You always should compare relative intensity between one phases and the other phases. You cannot measure one sample after other and compare them between themselves. You always should compare bands in the same spectrum, because the quality and intensity of your spectrum depend on a lot of things. For example, how you collimate your optics, what is, I don't know, temperature in the room, whatever. But when you have one spectrum, in this spectrum, it is reliable to compare two bands of different phases and also in the other. So from this ratio of the intensity, you will get calibration curve and later your results.
Yes, and just one more question. You mentioned that you have obtained that hexagonal phase in your barium titanate samples, and you said it was a surprise. But do you have some clues why it is?
This happened because of the preparation. The samples was first prepared with electrophoretic deposition. It was done in Slovenia. and then the samples was almost completely amorphous, and they were heated in the normal air enclosed circuit, but during this heating some oxidation happens. So this oxidation produce, or reduction, I don't know, they are chemists and they explain me that something happened during the heating. So during the heating these hexagonal lamellas was formed. They are normally stable only at the high temperature, but during the cooling of the sample after this heating, this lamella preserve in this there was multicrystalline.
So you think that the atmosphere is...
Yes, atmosphere influence this.
Thank you.
You're welcome.
Thank you for your talk. In one of your first pictures you showed possibilities of Raman. There were some vapors. So is it possible to measure Raman on vapors? And is it...
On vapors? Yes.
Yeah.
Yes.
How reliable are those measurements, and how difficult is the setup? I mean, if you're just... you probably need some concentrations of vapors, and what are the limits of those measurements?
So you always focus your laser beam in the part of the spectrum which you would like to measure. So example, if you have vapors in some vessel, you should focus your beam inside. So there is also one part of the measurement which was done in our laboratory. This wasn't my field of study. They did some kind, they call it matrix isolation. So they have inert some kind of, usually they use argon or even helium, and in this inert gas they insert very small amount of for example, water vapor or any other compounds, and they can study also rotational levels and so on. So very small amount of something you can measure with Raman spectroscopy, because you always focus your beam and you always have a focusing volume. So it depends what is your focusing volume. For example, you should do this measurement in the macro chamber to have larger volume of the focus, because if you focus in microscope, then your focus will be very thin and very small. So very small amount. I cannot tell you because it's not my main field of research, but it is.
Then is it possible to measure those Raman scatterings in flowing gases?
Yes, but I'm not sure how it will look like, because when you have something which flow...
Yeah, that's what I'm asking.
Maybe, I think so. I know one group in Berlin. I went usually going there for microscopy, but there is one group who do in situ catalysis and study it with Raman spectroscopy, and they do this catalysis in gas phases. So I suppose that it's possible, because they usually use flowing gases. They would not use such instrumentation if it's not possible. So,
thanks.
You're welcome.
Okay. Also, I have one, maybe two questions.
No problem.
You told in your presentation that we should be aware about the temperature.
Yes.
What is your opinion or your experience about the influence of temperature on observed Raman spectra when you perform your experiment on room temperature?
Okay, heating depends on the sample. Every measurement depends on the sample, of course. But if you have dark sample, for example, silicon, I had one example. I didn't speak about silicon, but I did a lot of experiments of nanocrystalline silicon. So in this case, we had amorphous matrix with very small crystals. So if you heat if your laser beam is high, during the recording of the spectra, you can see crystallization in the laser beam. So
in vivo.
In vivo, in vivo. So it's of course it's always depend on the sample. If you have a very light sample, white sample, then heating is not so strong. I didn't speak about heating temperature because they depend on the sample. If you have silicon, this was this example which my old boss did. Somewhere like here, yes. So he used silicon grains because of the reason that they are dark. So he, if he used only 20 milliwatts, he already have 200 degrees centigrade. So the heating was huge. But if you work, for example, with zirconium oxide or titanium oxide, they are white and heating is not so large. But you can always record Stokes and anti-Stokes part of the spectrum and calculate what is your temperature.
So why actually don't you use or maybe use a pulse laser with short duty cycle and
what? Pulse laser?
Pulse laser, not the continuous. Just lock the detections with some electronic equipment, PLL, phase lock loop, detect whenever you activate your sample, only then for short times.
As I know, pulse laser usually have much stronger power. So
yeah, but with short duty cycle, you know, it's high for 1% of the time.
Yes, you are right, but still, if you have a lot of pulses, I suppose that you will still have heating. And otherwise, I'm not sure how the spectrum would look like, because every time, if you have any changes of laser intensity during your measurement, then you will have changes in intensity of your band. So if you will have pulse laser, I have never think about this possibility because nobody uses pulse laser. I suppose that your spectrum will have also.
Maybe.
I don't know, but
maybe we got line or nothing. Just one line or nothing.
And, but in the pulse laser, you will have a change of the intensity. So probably your spectrum will look like this, like something.
Yeah, but as I said, you can use PLL. You can use lock to specific times. I mean, just in theory.
Good idea. I don't think about this because I always think our laser should be extremely stable. It should have very small line, very small, how to say, spectral.
Narrow
band.
Narrow band. But it's a good idea, but I suppose if it would be possible that producer would already produce such systems. Because
not always like that.
maybe they didn't have idea. Thank you. Maybe we can try to open spin-off firm to produce such systems.
Okay, thank you. One more question.
Yeah, the power of, for example, of X-ray diffraction is that you can assign the peaks for the back reflections by indexing them or even do a whole pattern fitting.
Yes.
How do you assign your peaks?
As I mentioned, you should do complicated calculation.
Well, that's not help us.
However,
usually
you use Raman spectroscopy and some well-known systems. You cannot use Raman spectroscopy for solve the structure. You can use Raman spectroscopy for complicated mineral to have idea which compounds do you have in your mineral. But later on you should do also some, I don't know, EDS measurement and so on. So this is one of disadvantages. I mentioned disadvantages that you haven't got direct insight. But a lot of work was done with Raman spectroscopy, and there is a huge amount of database with Raman spectrum for organic materials and organic minerals, whatever. So in my opinion, there is no sense to calculate. Some of my colleagues still calculate, but you can do calculation only for perfect system. You should have a continuous crystal, and you should use different approximations, so you always can calculate only perfect crystal. And most of us working at some nanocrystalline materials, polycrystalline, I don't know, some amorphous structures. So in my opinion, there is no sense to calculate, but it is possible. It is possible. Nowadays, there exist even some very user-friendly programs where you can put your data and they will calculate what you should expect in Raman spectroscopy. So this is also a possibility nowadays. But we haven't got direct insight. This is true.
Thank you again. Now we will have a short break again for